So again, welcome everyone to this first NTNU Energy Systems Seminar. We have Dimitri from aircraft for the BNPS group, and I'm Stefan, located here at IoT at BEDØK, optimization group. Previously, we've had seminars like this. Some people of you joined this 2 years ago, but we gave it a new life. And I think it's an excellent arena to just meet each other, have lunch, and somewhat informal, but also give other people the opportunity to join and listen to interesting presentations. We'll see how it develops, but we hope we can do this every other week, and hope to see you guys present someday. Today we have a presentation from Richard, a Ph.D. student here at Industrial Economics. And I don't think I'm going to give you a long introduction, but Richard, the floor is yours. And
thanks. So actually my real name is Hongyu, but I'm fine to be called Richard. Actually, I prefer Richard when I was a student, but then I think when I start PhD, the name on your paper is going to be your real name, not your nickname. So, so my name is Hongyu, and thanks for giving me the opportunity to present my work, and thanks for joining us in person and online. So in this presentation, I'm going to talk about the offshore energy hub concept in the energy transition. So this presentation is based on the following publications we try to finish. The first one is available online, and the second one will be available in June. So I want to start with the problem we try to understand. But firstly, I want to give you some background information. So as you know, the North Sea has huge offshore wind potential, and the green hydrogen is expected to be a big part of the possible massive hydrogen demand by 2050. And the recent Putin's invasion of Ukraine makes the EU surges toward energy independence, and renewables are given important role in this energy transition. And in addition to this, from Norwegian perspective, offshore oil and gas is the most important export commodities in Norway. And however, this sector has the highest emissions than any other industry in Norway. So it's an important sector to be decarbonized from Norwegian perspective. So all this come together leads to the questions we try to understand. So firstly, what are the values of offshore wind, offshore grid, offshore energy hubs, and green hydrogen in the energy transition? And then how can we make investment planning under uncertainty to fully decarbonize platforms and provide global insights? And you can see we're going to start with the offshore oil and gas decarbonization. And the reason we want to start from there is that this sector involves multi-billion-dollar investment and profits, and their decarbonization needs may likely trigger large-scale investment in offshore renewable technologies. So we want to understand what are the technologies exist, and how can we use these technologies to decarbonize platforms, and how can this invested assets to be used for energy export after the lifetimes of offshore field of the offshore fields. And so our motivation here is that eventually a mix of technologies can fully replace gas turbines here and achieve zero emission production. And the reason is that around 85% of the emission from the oil and gas platform is coming from the energy provision, And to replacing gas turbines with emission-free technology is an effective way to decarbonize the platforms. And our motivation to consider offshore energy hub is that there is a weight and space limitation of the platforms, so it may be technically infeasible to make any modification of the platforms. So an external hub to help efficiently distribute offshore wind may be a promising option. And a more major function of offshore energy hub is to export clean energy to the onshore system for the energy transition. So these are our motivations. And now I want to give you two more pieces of background information to follow the presentation. First is on the methodology. So we are going to deal with an investment planning problem over a long planning horizon. So this you will face uncertainty from both operational level and strategic level. So to include both uncertainty in a model, in a stochastic, a multi-stage stochastic model will lead to a large scenario tree. But for a model like this, with long planning horizon, you don't actually need to plan your system operation for decades ahead. Instead, you probably only are interested in examining your investment decisions with some operational constraints. So that is why we go for multi-horizon modeling approach. And then secondly, I want to talk about the offshore energy hub. So offshore energy hub is a unit where multiple energy carriers can be converted, conditioned, and stored. So different energy hubs will have quite different configurations. And in our study, we consider a hub that can take offshore wind power and convert this wind power to hydrogen and store the hydrogen in some form, either a tank or underground formation. And then this hydrogen can be reconverted to electricity via fuel cells. So here I want to point out that strictly speaking, an energy hub should have the function of storage. Otherwise, this hub is more of a power distribution and power generation hub. However, in the context of an offshore energy system, a lot of literatures, they consider this offshore energy hub without considering storage. So strictly speaking, this thing shouldn't be called energy hub, or rather to be called power generation distribution hub. But in our study, we consider the three functions, all three functions. And now I want to talk about the specific problem we try to model and solve. So the problem is an investment planning problem of the decarbonized North Sea offshore energy system, considering the connection and interfaces with the European onshore energy system. And we consider the investments in a bunch of technologies, including offshore renewable energies, offshore energy hubs with electrolyzers, hydrogen storage, and fuel cells, and converters, and subsea cables, and electric boilers, which is important for replacing gas turbine. And then we consider also platform-located batteries, which may be feasible for many platforms due to the weight and space limitation again. And also we consider the power system expansion on the onshore system, including the generation, storage, and transmission. And the model is going to decide what is the optimal capacities of the technologies, and what are the optimal operational strategies based on your investment decisions. And the objective is to minimize the overall costs. So now I want to give you, and now I want to give you an idea of what is the scale of the study and how what the strategies we use to keep the problem a reasonable size. So as you can see, we are going to consider the entire European energy system. However, this will lead to potentially lead to a very large model, and that is why we use some aggregation method to represent the geographical structure of the system. And as you can see, we aggregate the onshore system into some representative node because our focus is in the offshore system. And we have a relatively more detailed representation of the North Sea offshore system. And we have a bunch of offshore fields here in the Norwegian continental shelf. And we aggregated them into several representative locations. And in addition to geographical representation, we also need to think about the temporal representation of the system, because this problem is going to be, the planning problem can span over a long time horizon. So if you examine your investment decisions over all the operational hours in a year, it will lead to a very large problem. That is why we selected some time intervals from that year and scaled them up to represent the full operational year. So you can still capture the system operation in different time intervals without really run your models over all hours. And also this the process the process of the fluids and gas on the platform can lead to nasty equations. So that is why we take some typical values in the North Sea so that we can have a linear formulation. And now I want to talk about the model we developed for this problem. So it's a stochastic MILP model. So we're going to, it's a multi-period stochastic MILP model with high degree of operational details. And then the objective is to minimize the overall costs. And we have integer variables in the investment planning part, which is important because you're going to capture the economic scale of your investment. If you only have a linear cost model, you cannot capture the fixed part of the investment. And then all the operational constraints are linear, and we have multiple energy carriers in the model. And we'll just very quickly go through the mathematical formulations. So as you can see, the objective is to minimize the overall investment and operational cost. And equation 1b calculates the investment related cost. And equation 1c make sure that the available capacity at one operational node is equals the historical capacity plus the investment you made in its previous investment nodes, excluding the one that are retired. And you have some maximum capacity constraints, 1D and 1E. And now I want to go through very quickly about the operational constraints. So again, this constraint 2A calculates the operational costs. We have a bunch of capacity limits, and then you have ramping limits of thermal generators, and then you have reserve requirement, and also the power and heat, power balance, heat balance, and hydrogen energy balance. And we have the storage balance of storage facilities and the CO2 budget. So the investment is driven by CO2 budget and CO2 cost. So we use this model to conduct case studies on, firstly, in the North Sea part of the Norwegian continental shelf. We consider all the 66 offshore fields that are operating in the NCS. And we consider a fairly simple network topology. As you can see, we only draw one line from from shore to support supply power to offshore, and there are no interconnections among the offshore locations. And using this model, we conducted sensitivity analysis on 3 parameters, including CO2 tax, CO2 budget, and the capacity of power from shore. And for the sake of time, I will only go through the results of sensitivity analysis of CO2 tax. So to do this, we increased the CO2 tax from the current level, around 55 euro per ton, to 500 euro per ton, with a step size of 5 euro per ton. And as you can see from this plot here, even you increase CO2 tax to 500 euro per ton, you still have around 250,000 ton emissions in your system. So I think my insight from here is that CO2 tax alone may not be enough to motivate a zero emission system. And then if you compare the 2 lines, the red line, blue lines, you can see that in a system with offshore energy hubs, it can potentially reduce up to 50% more CO2 emissions and 5% total cost. And here I want to mention we put a huge fixed investment cost of the offshore energy hub. So it's going to be costly to have this hub. That is why it doesn't show much economic benefits of having an offshore energy hub. But still, it can reduce the costs a little bit. And we also analyzed the results from another matrix, the energy loss. So because this is something missing in the literature. So having this hub, meaning that you are going to convert and reconvert these different energy carriers, and it's going to cause energy loss. And but how much it will be, it may be, and it's not clear. So we also analyze this, and you can see, although there will be energy loss in the energy hub, but overall it will help to reduce 10% more in terms of energy loss. That is because if you don't have an energy hub, there is a lot of wind power is going to be shed, the green part here. And that is much more compared with the loss that occurred in the offshore energy hub. Then we expand our understanding of the system to include the entire European energy system. So as you can see, we still keep a very detailed modeling of the offshore system. We have a lot of several potential locations for offshore energy hub, and we use this model to analyze what are the potential values of offshore energy hubs in the energy transition, European energy transition. So I think I want to show you this result here. As you can see, the orange line, the orange line is the emissions from the Norwegian continental. Yeah, please. Oh, yeah. Okay. So I will be real quick here. So I think one insight from this result is that the first half of the emission from the Norwegian continental shelf is going to be, it seems to be cheaper compared with the first half of EU emissions, but it's going to be more expensive to achieve a zero emission offshore energy system compared with the onshore system. And I think now I want to show you this network topology here. I think one insight from this result is that the offshore grid seems to be very important in this energy transition, especially 2040 seems to be a turning point that a lot of offshore locations are being connected. I will skip this slide here. So the main conclusions from these 2 papers is that offshore energy hubs may have values in emission reductions, energy losses, and costs. And a hard carbon cap may be necessary to to enable a zero emission system. And then I think offshore grid design may be very crucial for this energy transition. And some future work here, as you can see, actually in the second case study, the electrolyzer is not invested, and that is because it's very expensive to have this without including hydrogen demand or hydrogen market. So in future, the next step we're going to do is to include a hydrogen demand in the model, and also we want to include the repurposing of the oil platforms, and also there is a massive underground storage capacity which can be interesting to include it, and also carbon capture and storage. So that's all I want to present, and yeah, I omit a lot of details, but yeah, we can discuss this. Yeah, and okay, these are the some literature. Yeah, thanks.